get ready to dive deep into machining work-holding systems.
Sounds good.
You know, you sent me all these excerpts from this Romanian textbook
Right.
called Machining Work-Holding Systems.
Okay.
And, man, it's pretty intense stuff.
Yeah,
I gotta say.
it is.
So basically, you're looking for just the fundamentals of work-holding systems, right?
Yeah, just the basics.
And I'm so glad you're here to help me kind of unpack all of it because, especially since it's all in Romanian.
Well, thanks for having me. It's my pleasure. Work holding is such a fundamental aspect of machining.
Right.
And it's always interesting to see how, different texts kind of approach the subject, right?
Yeah.
Yeah, different ways of thinking about it.
Exactly. So what we're going to do is we're going to explore, how these systems, how they make sure everything stays stable and precise during the machining process.
Right.
We're talking lathes, milling machines, all that good stuff.
Exactly.
Now, the book dives into work-holding systems for both cutting tools and workpieces, right?
Yes, exactly. You can't really have one without the other.
Right.
They both play a critical role
Okay.
in achieving accurate and safe machining.
Okay. So let's start with the cutting tools.
Okay.
The book talks about this evolution, right?
Yeah.
From brazed inserts to these removable ones called vidia.
Yes.
What's the story there?
Well, brazing, that was the go-to method
Right.
for a while. But, it had its limitations.
Okay.
It was time-consuming
Yeah.
and not very flexible. You know what I mean?
I got it.
And then came these removable inserts.
Right.
And there was this company, Widia,
Okay.
and they really kind of made their mark.
Got it.
And their inserts were so good that the name Widia just kind of became synonymous with cutting inserts.
Oh.
Kind of like how we use Kleenex for tissues.
Oh, okay. I can see how that happens.
Right. Just like,
yeah, that makes total sense.
it's just what everybody calls it.
Yeah, it's like the
name stuck.
name stuck. Yeah. So is Vidia just a brand name, or is there something special about these inserts?
Well, it started as a brand name.
Right.
But the name itself is actually a clever acronym.
Oh.
It stands for Widia Inserts and Drills in Action.
Oh, wow.
And they actually pioneered this use of these centering screw systems,
Right.
which was really a game changer
Okay.
for both efficiency and precision.
Okay, so let's break down those centering screw systems. What makes them so much better than brazing?
Well, imagine you're working on a project, right?
Yeah.
And your cutting insert wears down.
Okay.
If you're using brazing, you're going to spend a lot of time removing and replacing the entire tool.
Yeah.
With a centering screw system, you simply unscrew the old insert, pop in a new one, and boom, you're back in action.
Got it.
So it really reduces that setup time.
Yeah, that's a huge time saver,
Huge.
especially in like a busy shop.
Oh, yeah.
But the text goes on and on about the importance of using proper torque
Oh, yeah.
when you're tightening those screws.
Absolutely.
Yeah.
It's crucial.
So why is that so important?
Using the correct torque, it's super important.
Yeah.
It's crucial for maintaining the stability and the tool life.
Right.
Think of it like Goldilocks and the Three Bears.
Uh-huh.
You don't want it too loose or else the insert's going to come flying out.
Yeah.
But you don't want it too tight because then you could damage the tool
Right.
or the workpiece. It needs to be just right.
So what's the best way to make sure you're hitting that sweet spot?
A torque wrench.
Torque wrench.
That is your best friend.
Okay.
It's going to allow you to apply just the right amount of force
Right.
that the tool manufacturer recommends.
Got it.
It's a small investment,
Okay.
but it's going to save you a lot of headaches down the road.
Noted.
Yeah.
So we've got those cutting tools locked and loaded.
All right.
Now let's talk about how we hold the workpiece itself,
Okay.
starting with lathes.
Lathes, yeah.
And the book really gets into chuck systems,
Right.
those things with the jaws
Yeah.
that clamp onto the material.
Right. The jaws are like the strong hands of the lathe.
Right.
They're gripping the workpiece firmly
Yeah.
as it spins.
Okay.
They're essential for so many turning operations.
Right. But there are different types. Yeah.
Oh, yeah, absolutely.
The book mentions 3-jaw and 6-jaw chucks.
Yes.
And even this Romanian study
Right.
that used computer simulations to compare them.
That study is super interesting. They use something called finite element analysis,
Okay.
which is basically a way to model how forces and stresses affect a structure.
Okay.
And they showed that 6-jaw chucks, they're much better at holding thin-walled workpieces
Got it.
without distorting them.
Okay. So that's interesting. So if you're working with delicate, thin-walled parts,
Right.
6-jaw chuck is the way to go.
It's definitely something to consider.
Okay.
And speaking of considerations, The book emphasizes checking the lathe's power chart
Yeah.
before you start clamping anything down,
Yeah.
because it's going to tell you what the appropriate clamping power is for different materials and sizes.
Yeah, that makes total sense.
Yeah.
You don't want to over-tighten and damage something.
Exactly.
Now, the text goes into a lot of detail about positioning those juck jaws.
Right.
And they even use this term arc of contact.
The arc of contact, well, it basically refers to the portion of the workpiece that's actually in contact with the jaws.
Got it.
And if that arc is too small, you don't have a secure grip,
Right.
and the workpiece can slip.
Okay.
If it's too large, you run the risk of the jaws interfering with the cutting tools,
Oh.
or even getting tangled up in the chips.
So you need to find that Goldilocks zone again,
Great.
right?
Got it.
Not too small, not too large.
Not too small, not too large.
Right.
Precisely. And here's a funny little tip from the book.
Okay.
If you grind the inner corner of a chuck jaw incorrectly,
Yeah.
it can actually push the workpiece outward instead of clamping it down. It's kind of counterintuitive, but it shows you just how important those subtle details are.
That's wild. It's like a reverse chuck. It seems like those jaws can cause a lot of trouble if they're not set up just right.
They can, and it's a good reminder
Yeah.
that even seemingly simple tools require careful attention to detail.
Right.
Now, while chuck systems are great for many lathe operations,
Yeah.
they're not always the best choice, especially for smaller workpieces.
Okay.
The book talks about collet systems as an alternative.
Collet systems.
Yes.
Okay, I'm intrigued. How are those different from chucks?
Well, think of a collet as like a precision sleeve
Okay.
that wraps around the workpiece.
Got it.
It provides a very secure grip,
Okay.
and it really minimizes distortion, especially for delicate parts.
Ah, so they're kind of like the gentle giants of work holding.
Yeah, that's a great way to put it. They're also great for high-speed machining because they're so well balanced.
But no matter what system you're using, safety is paramount.
Of course.
Yeah.
Absolutely.
Okay.
Safety first.
The book even has a whole section on general safety instructions, reminding us to be mindful of things like spinner rotation, pressure, and even what to do if the power goes out.
Yeah, those are all crucial points. Safety should always be the top priority in any workshop.
Totally agree. So let's say I'm tackling a new project. How do I know if I should reach for a chuck or a collet system?
It really depends on a few factors.
Okay.
So for smaller workpieces, a collet system is often the better choice
Okay.
because of the precision and the ease of use.
Right.
But for heavier or larger workpieces, you probably need that robust clamping power of a chuck.
Right. Right.
And of course, you need to consider the capabilities of your lathe itself.
the lathe itself.
The lathe.
The right tool for the right job.
Always.
Right. Now, there's another challenge the book brings up, and it has to do with the forces at play when a workpiece is spinning in the lathe.
You're talking about centrifugal force.
Centrifugal force, right?
Yes, as that workpiece spins faster and faster. Centrifugal force is trying to pull that material outwards.
Okay.
And this can cause the workpiece to kind of rotate off-center.
Okay, I see the problem. It's like trying to balance a spinning top.
Right.
Right.
Exactly.
If it's not perfectly centered, it's going to wobble all over the place.
Exactly. And
Yeah.
to counteract those centrifugal forces, the book suggests using multi-arm clamping devices.
Okay.
Things like 6-arm sockets.
So instead of just clamping down from two sides,
Uh,
you're applying pressure from multiple points to keep everything centered.
That's the idea.
Okay.
And speaking of stability, the book introduces this general rule
Okay.
that's based on something called the LD ratio.
Okay.
That's the length of the workpiece divided by its diameter.
Okay.
And this ratio, it can help you figure out when to use a chuck, a steady rest, or a follow rest on your lathe.
LD ratio. All right, I'm all ears.
So the general rule, if that LD ratio is less than 3, you can probably get away with just using a chuck.
Okay.
But as that ratio increases, that workpiece becomes more prone to bending and vibration.
Wow.
You need to add more support.
So it's like adding training wheels to a bike.
Yeah.
Right.
Hmm.
The longer and thinner the workpiece,
Exactly.
the more support it needs.
Exactly. So for an LD ratio between 3 and 6, the book recommends adding a steady rest,
Okay.
which basically provides support in the middle of the workpiece.
Got it.
And as that ratio gets even higher, you might need a follow rest, which supports the workpiece right behind the cutting tool.
Okay. That makes sense. So it's not just about clamping it down. You also have to think about how to support the workpiece along its length, right?
Exactly,
Yeah.
especially when it's long and slender.
Yeah.
And keep in mind, this LD ratio rule, it's just a guideline.
Right.
The specific material you're working with,
Yeah.
the cutting forces involved, the type of operation you're performing,
Right.
All those play a role in determining how much support you need.
Solid advice.
Mm.
So listeners, keep that LD ratio in mind, but always use your best judgment and err on the side of caution.
Exactly. It's better to have too much support than not enough.
Yeah. Now we've covered a lot of ground with lathe work holding. Ready to move on to milling machines?
Absolutely. Milling machines, they present their own unique set of work-holding challenges and solutions,
Right.
and I'm eager to explore them.
Perfect. Because I have a feeling things are about to get even more interesting.
Oh, yeah.
Okay.
When it comes to milling machines,
Yeah.
the conversation often starts with those T-slot channels you see on most milling machine tables.
Ah, yes. The trusty T-slots.
Yeah.
They seem pretty straightforward, but the book does point out some drawbacks.
Well, they're definitely robust,
Okay.
but they can be a bit of a pain when it comes to chip accumulation.
Right.
You end up spending a lot of time cleaning them out.
I can relate to that.
Yeah.
It's like they're magnets for metal shavings.
Exactly. What's the other issue?
Yeah, what is it?
Well, precise repositioning.
Okay.
It can also be tricky with T-slots. If you have to remove a fixture and then try to put it back in exactly the same spot,
Yeah.
it can be a real challenge.
I can see how that would be frustrating,
Yeah,
especially if you're working on a project that requires high precision.
absolutely.
So does the book offer any solutions?
It suggests making sure those channels are perfectly parallel
Okay.
to the axis movement of the machine.
Right.
You might need to do a little machining
Right.
on the table itself
Got it.
to get it just right.
Yeah.
But it's worth it for that improved accuracy.
Okay, so a little preventative maintenance can go a long way.
Absolutely.
Now, aside from T-slots, what are some of the other methods for securing workpieces on a milling machine?
Clamps and vices.
Okay.
They're incredibly versatile,
Right.
especially for those oddly shaped workpieces
Yeah.
that don't fit neatly into a standard setup.
The book specifically mentions stepped clamps,
Yes,
which seem like a clever way to use those T-slots to your advantage.
they are.
Okay.
And it even offers a couple of practical tips. First, try to keep the clamp screw as close to the workpiece as possible.
Uh-huh.
This reduces leverage.
Got it.
It makes for a more stable setup.
Simple but effective.
Exactly.
What's the other tip?
This one's kind of funny.
Okay.
The book suggests using a piece of a soda can
A soda can.
between the clamp and the workpiece to prevent scratches.
Oh, that's interesting.
It's low tech, but it works.
That's a good one. I like those little workshop packs.
Me too.
Okay, so we've touched on clamps. What about vices?
Vices.
They seem to be a staple in any milling machine setup.
They're the workhorses.
Right.
The book delves into two main types,
Okay.
single vice and double vice holding.
Got it.
Both provide a secure grip,
Okay.
but they can be a bit tricky when you're dealing with those complex workpiece shapes.
Makes sense.
Yeah.
And I noticed the book mentions Kurt vices.
Ah, yes, the classics.
Those classic cast iron ones.
They've been around forever.
Yeah.
And for good reason.
Right?
A well-made vice
Yeah.
should operate smoothly, be repeatable.
Right.
And it should have a mechanism that prevents the workpiece from lifting
Okay.
when you tighten those jaws.
So it's all about those little details
All those details.
that make a big difference in performance.
They really do.
Does the book have any advice
It does.
on setting up a vice properly?
It walks you through the steps,
Okay.
starting with making sure that milling machine table is clean
Right.
and the vice is aligned,
Got it.
and using an indicator.
Yeah.
That's the best way to make sure that alignment is spot on.
Okay, so cleanliness and alignment are key.
Absolutely.
What's next?
Well, the book suggests using parallels or step jaws
Okay.
to raise the workpiece up a bit.
Got it.
This gives you better access
Right.
for your cutting tools,
Okay.
and it also helps with repeatability.
Got it. Any other tricks up its sleeve?
Here's a clever one.
Okay.
If you need to hold a larger plate,
Yeah.
you can actually mount the vice jaws outside their normal position.
Interesting.
It's a great way to maximize space. Yeah.
On that milling machine table?
Space optimization is always a win
It is.
in a workshop.
For sure.
It's like playing Tetris with your tools and workpieces.
Exactly. And it's not uncommon to see multiple vices
Right.
on a larger milling machine.
Okay.
It's an efficient way to machine multiple parts before having to reload.
That's smart.
Yeah.
So if you're going the multi-vice route, are there any recommendations?
The book emphasizes the benefit of using identical vices
Okay.
for consistency.
Got it.
And if you have vices that are slightly different,
Yeah.
you can always use a surface grinder
Okay.
to adjust them so they match perfectly.
Okay. So consistency is key when you're dealing with multiple setups.
It really is.
Now, I'm curious about magnetic chuck holding.
Oh, yeah.
Those always seem kind of magical to me.
They are pretty magical. They can be incredibly fast to set up.
Yeah.
The book highlights their ability to apply uniform clamping force
Okay.
across that entire workpiece.
But I'm guessing there's a catch.
There is.
Magnetic chucks only work with materials that are attracted to magnets.
Right.
Things like steel and iron.
So not quite magic,
Not quite.
but still pretty cool.
Still pretty cool.
Now, the book also mentions rotary table holding,
Yes.
which seems like a way to add another dimension of movement
It is.
to the milling process.
It is all about rotating the workpiece
Okay.
during milling.
Right.
It allows you to access different surfaces without having to manually reposition it.
So instead of just moving the cutting tool,
Right.
you can also rotate the workpiece to achieve more complex cuts.
Precisely.
Okay.
And the book differentiates between two main types.
Okay.
Those that are mounted directly on the CNC machine table,
Right.
which offer 1 degree of freedom,
Okay.
and those that replace the entire machine table,
Got it.
which provide 2 degrees of freedom.
So the first type is for simpler 3+1 axis milling,
That's right.
while the second is for the more complex 5-axis machining.
Exactly.
Okay.
And 5-axis machining actually requires special vices.
That can clamp securely,
Right.
but also take up minimal space on that machine table,
Right.
because those rotary tables can be quite large.
It's amazing how much thought goes into optimizing these systems for efficiency and precision.
Oh, yeah. It's incredible.
Now, I'm really intrigued by the book's mention of rotary tower holding.
Rotary towers.
It sounds like it takes efficiency to a whole new level.
They're like having a whole arsenal of milling tools at your fingertips.
Right.
They're essentially multi-tool turrets for milling machines.
Okay, I'm picturing something like a revolving spice rack, but for cutting tools.
That's a great analogy.
Right.
The tower holds a variety of milling tools,
Yeah.
and it can quickly rotate
Okay.
to bring the desired tool into position for machining.
So it eliminates all that time spent manually swapping out tools.
Exactly.
Yeah.
It's a huge productivity booster,
Yeah.
especially for high-volume manufacturing.
And the book even mentions the possibility of automating the pallet or tower changing process.
Oh, yeah.
That's next level automation. It is
Right.
automated systems like that can dramatically reduce machine downtime,
Right.
which is a major factor in optimizing that whole production flow.
Okay. Color me impressed.
It's pretty amazing.
Now, the book also talks about a method called holding with centering bolts
Right.
or drawbars.
Yeah, it's a similar concept to how those milling cutters are held in the spindle.
Right. It sounds a lot like that.
Yes.
Right.
This method uses a drawbar to pull the tool holder into the spindle,
Okay.
creating a tight and secure connection.
Got it.
It's essentially the same principle, but applied to holding the workpiece itself.
So you're using a similar mechanism to hold both the cutting tool and the workpiece.
Exactly.
Clever.
It is.
And the book points out that this method works well
Yeah.
for smaller or lighter workpieces
Yes.
that don't require those super strong clamping forces.
Exactly.
Okay, so it's a good option for those more delicate milling operations.
It is.
Wow, we've covered quite a range of work holding methods for milling machines.
We have.
I'm starting to appreciate just how many options are out there.
There is a wide array of solutions out there,
Yeah.
each with its own strengths and weaknesses.
Now let's shift our focus back to lathe tools
Okay.
and the systems used to hold them.
All right, back to the lathe.
Back to those spinning wonders.
Yeah.
I remember the book talked about turrets and tool blocks.
Yes, and the book points out that turrets, they're particularly prevalent on CNC lathes.
Okay.
They're essentially rotating tool holders
Got it.
that can be indexed to bring different tools into the cutting position.
So they're like little tool carousels,
Exactly.
ready to deliver the right tool for the job.
Precisely.
Right.
And the whole process is controlled by the CNC program,
Okay.
allowing for very rapid and precise tool changes.
And that's how CNC lathes achieve those impressive speeds and complex machining capabilities.
Precisely.
Right.
However, turrets can be more expensive
Okay.
than traditional tool blocks,
Right.
and they might require more sophisticated programming.
Okay. To really utilize their full potential.
So there are trade-offs to consider.
There are
What about those tool blocks?
tool blocks.
Where do they fit in?
Well, they're much simpler
Okay.
and often found on manual lathes.
Nice.
Or they're used for very specific operations.
Okay.
They typically hold just one or a few tools,
Got it.
and they don't have that indexing capability of a turret.
Okay. Simpler to use,
Simpler.
but less versatile
That's versatile.
than a turret system.
Exactly.
The book also goes into detail about different tool holding methods within those systems.
Right.
It talks about rectangular shank holding,
Yes.
which is common for external turning tools.
Very common.
Yeah.
Rectangular shank holding is very straightforward.
Okay.
The rectangular shank of the tool fits into a corresponding slot in the turret or the tool block.
Got it.
It's a tried and true method.
Tried and true.
Been around forever.
And I like how, rather than just like listing out
Yeah.
all the available shank sizes,
Right.
the book actually explains the why.
The factors that influence which size you'd choose.
Absolutely.
Right.
The size of the tool,
Okay.
the material you're cutting,
Right.
the forces involved,
Yeah.
all of those things play a role.
So it's not a one-size-fits-all situation.
Not at all.
What about holding those internal turning tools?
Internal turning tools.
Is there a specific method for those?
The book focuses on the bushing system
Okay.
for internal turning tools.
Got it.
The tool is held securely in a precisely machined bushing,
Oh, okay.
which then fits into the turret or tool block.
And of course, those bushings come in various sizes and shapes to accommodate all sorts of different internal turning tools.
Precisely.
Yeah.
It's all about creating a secure and stable connection
Yeah.
for those internal machining operations.
Right now, remember how we touched on VDI earlier?
VDI.
The book goes into a lot more depth
Much more.
about this system,
Right.
which seems to be a big deal in the CNC lathe world.
It is a big deal.
Right.
VDI stands for Verein Deutscher Ingenieur,
Okay.
which translates to Association of German Engineers.
Association of German Engineers.
But yes,
Yeah.
it's a widely used standard
Okay.
for tool holding on CNC lathe turrets.
A German engineering standard.
That's right.
That definitely piques my interest.
It should.
So what are the key advantages of using VDI?
Well, the book highlights 3 main benefits.
Right.
First, VDI makes tool changes very quick and easy,
Okay.
thanks to its quick release system.
Got it.
Second, its precise geometry
Yeah.
and clamping mechanism
Yeah.
ensure rigid and accurate tool holding.
Right.
And third, there's a wide variety of compatible tools and accessories available,
Okay.
so you're not limited in your choices.
So it sounds like a winning combination.
It's a winning combination.
How does the actual coupling system work?
It uses a taper
Okay.
and a clamping nut to securely mount the tool.
Got it.
It's a very efficient and reliable system.
Okay.
And the book emphasizes the importance of VDI-driven tools
Thank
for operations like milling and drilling on CNC lathes.
Okay.
Because those VDI-driven tools,
Yeah.
they can be controlled in both rotation and position
Right.
by the CNC system,
Right.
which allows for true 360-degree machining of that workpiece.
So it really expands the capabilities of a CNC lathe.
It really does.
It's like having a lathe that can also function as a milling machine.
Exactly. The lines are getting blurred.
The lines are getting blurred, yeah.
Technology is amazing.
Technology is amazing.
Right.
Now, remember, the book also compares
Yes,
BMT and VDI tool holders.
it does.
Can you walk us through the key differences between those two?
Of course. BMT, which stands for base-mounted turret,
Okay.
is generally considered to be more rigid.
Got it.
It's typically mounted on the turret face
Right.
using 4 hex screws,
Okay.
and it often has a key for precise alignment.
So it's simple, robust, and easy to align.
Exactly.
What about VDI?
Well, VDI, on the other hand,
Yeah.
uses a serrated shaft and a clamping mechanism that requires careful indication during mounting.
Got it.
There's a little bit more potential for rotation
Okay.
during the mounting process,
Right.
so you have to be more precise to
Sure.
avoid alignment issues.
So VDI demands a bit more finesse during setup.
A little bit.
The book even jokes about VDI standing for very difficult to indicate.
It does.
But despite that extra care required for setup,
Right?
VDI offers greater precision and adjustability once it's properly mounted.
Exactly. A little more work up front,
Right.
but potentially higher precision in the long run.
Are there any other key differences?
Well, a big one is that VDI holders can be mounted
Yeah.
on either the turret face or the circumference,
Okay.
whereas BMT is typically limited to just the turret face.
Got it.
That gives VDI more flexibility in terms of tool placement.
Yeah, that makes sense.
Right.
More mounting options mean more versatility when you're dealing with complex tool setups.
Absolutely.
And to illustrate that versatility,
Yeah.
the book gives an example of a turret with 12 stations
Right.
that can actually support 36 different cutting tools
Yes.
through clever design and tool organization.
Clever design.
Wow, that's a lot of tooling power packed into one turret.
It is.
So the choice between BMP and VDI really comes down to
It does.
the specific application and the desired level of precision.
Absolutely. And it highlights the creativity
Yeah.
and the problem-solving skills of the engineers who develop these systems.
Now let's zoom in on milling tool holding systems,
Milling tool holding.
where colettes play a starring role.
Yes, they do.
The book does a great job of explaining those key components.
Right.
The drawbar, the collet itself, the retention knob, and even those Belleville washers.
All those components.
It's amazing how those seemingly simple components
Yeah,
all work together
they do.
to create such a precise and secure connection
Right.
between the tool and the spindle.
It is fascinating.
Shall we break down the function of each part? I'm especially curious about those Belleville washers.
Oh, yeah.
They look like little dish-shaped springs.
They do.
Right.
And their purpose is to maintain consistent clamping force
Okay.
and to compensate for any slack in the system,
Got it.
ensuring that the tool is held securely even as temperatures change
Right.
during machining.
Okay, so they're like the unsung heroes of the collet system,
They are
working diligently to maintain stability.
behind the scenes.
What about the other components?
Well, the drawbar is the muscle.
Okay.
It pulls the tool holder into the spindle
Right.
to create that initial connection.
Okay.
And the collet itself, with its conical shape,
Yeah.
grips the tool shank tightly,
Right.
converting that axial force from the drawbar into radial clamping force.
And then there's that retention knob.
The retention knob.
What's its role?
The retention knob makes tool changes easy.
Okay.
It acts as a quick release mechanism,
Got it.
and it also helps secure the drawbar in place.
Okay, so it's all about ease of use and safety.
It's exactly.
Now, the book talks about ER collets being the most popular type
They are the most popular.
for milling machines.
Yes.
But it doesn't really explain why.
Yeah.
Can you shed some light on their dominance?
They've earned their popularity for a few reasons.
Okay.
First, they were standardized
Okay.
under DIN 6499,
Got it.
which ensures consistency and compatibility
Right.
across different manufacturers.
Standardization, always a good thing in the world of engineering.
Always a good thing.
Right.
Second,
Yeah.
they're incredibly versatile.
Okay.
They come in a wide range of sizes
Right.
to accommodate various tool shank diameters.
Got it.
And third, their clamping mechanism is very effective and reliable,
Okay.
providing a really secure grip
Right.
that's essential for those precise milling operations.
And I like how the book explains that ER designation.
Oh, yeah.
It actually comes from an earlier E-type collet
It does.
that was modified by a company called RegoFix.
That's right. And the number in that ER designation actually corresponds
Okay.
to the collet's opening diameter in millimeters.
Got it.
So an ER20 collet has a 20 millimeter opening diameter.
That makes perfect sense.
It does.
The book also mentions that a complete set of ER collets
Right.
with those 1 millimeter increments
Yeah,
can handle pretty much any cylindrical diameter within the series capacity.
pretty much.
That's impressive coverage.
It is.
Right.
And they even make ER collets
Okay.
with inch-based internal dimensions
Got it.
for those working with imperial-sized tools.
So they thought of everything.
They really have.
What about other types of collets?
Oh, other types.
I remember the book briefly mentioned R8 and 5C collets.
R8 and 5C?
Yeah.
Well, R8 collets are often used in milling machines,
Okay.
while 5C collets are more common in lathe applications.
Okay.
They each have their own specific advantages
Right.
and are chosen based on the machine and the tooling you're using.
So it's all about matching the collet to the task at hand.
It is.
Now, this next part is particularly fascinating. Okay. The book talks about specialty and custom collets.
Oh, yeah.
It seems like some machinists get really creative.
They do. Some manufacturers have their own dedicated collet systems.
Okay.
And there's even a practice of making custom collets.
Wow.
Sometimes called emergency collets or soft collets
Okay.
for really unique workpiece shapes or sizes.
So they're like the master tailors of the machining world,
That's a great way to put it.
creating the perfect fit for every situation.
It speaks to their ingenuity
Yeah.
and their resourcefulness.
Now, before we wrap up this work-holding exploration,
Okay.
we need to talk about power chucks.
Power chucks.
They're a powerful alternative to collet systems,
They are.
especially for those larger workpieces
Right.
that require a little more muscle.
They need that extra clamping force.
I'm ready for the power chuck deep dive.
Let's do it.
What makes them so special?
Power chucks.
Yeah.
It's all about brute strength
Okay.
when it comes to clamping force.
Right.
They were actually developed back in the 1940s.
Oh, wow.
As a more efficient and powerful alternative
Right.
to those traditional key-operated chucks.
So more clamping power.
More clamping power.
And less manual effort.
Less manual effort.
I can see the appeal.
Right.
How do they work their magic?
They typically use either hydraulic or pneumatic systems
Okay.
to generate that incredible clamping force.
Got it.
It's a significant step up in terms of both power and control.
And the book mentions that power chucks can be automated,
Oh, yes.
which opens up a whole new world of possibilities for efficiency.
It does.
Right.
Automated power chucks are a key component
Yeah.
in many advanced manufacturing setups.
And just like with the other work holding systems we've discussed,
Right.
there's a wide variety of power chuck types and sizes available,
There is.
allowing you to customize your setup based on the specific machine and workpiece requirements.
That's the beauty of it.
Okay, so lots of options to choose from.
Lots of options.
I have to say, this deep dive has been incredibly informative.
I'm glad to hear that.
I feel like I've gone from work holding newbie
Good.
to having a solid grasp of the fundamentals.
That's great.
But there's one more crucial area
Yes.
we need to explore before we wrap things up.
One more.
Taper standards and tool holders.
Taper standards.
Right.
Very important.
Let's get into it.
Taper standards are all about ensuring that tool holder fits snugly and securely in the machine spindle.
Okay.
They've evolved over time
Right.
to meet the demands of, increasingly sophisticated machining operations.
All right, let's talk taper standards.
Yeah.
The book throws a lot of acronyms at us. Shikate, BT, JIS, DIN, ISO. It's a little overwhelming.
I know it can seem like alphabet soup at first.
Right.
But each of these standards, they represent a specific approach.
So it's not just about grabbing any old tool holder.
Right.
There's a whole world of compatibility to consider.
Exactly. Compatibility is key.
Let's start with what's most common here in the U.S. CAT, which stands for Caterpillar. It seems a bit odd to see a construction equipment company name pop up in the machining world.
It does, doesn't it?
Yeah.
But CPAT holders, which are also known as ASME B5.50,
Yep.
they're known for their V-shaped flange
Yeah.
and their robust clamping mechanism. They're real workhorses.
And the book mentions that they can handle both metric and imperial threads.
That's right.
That's pretty handy when you're choosing tools.
Absolutely. That kind of flexibility is always appreciated
Yeah,
in a workshop.
for sure. Now, another popular standard is BT, which originated in Japan.
Yes.
It stands for Big Plus Tooling System.
Big plus.
Big Plus. That sounds pretty self-explanatory.
It does, right?
What makes them stand out?
Well, BT holders are known for their symmetrical flange,
Okay.
which gives them excellent stability, especially at high speeds.
Got it. And they use metric thread studs or drawbars for connecting to the tool holder. So metric threads for a Japanese standard. That's interesting.
It is.
Right. The world of machining is full of little surprises like that. Now, the book also mentions JISB 6339.
Okay.
That's the Japanese standard for collet chucks.
And it sounds like JIS holders are pretty similar to BT holders in terms of features and dimensions.
You're right. They do share a lot of similarities.
Okay.
Both standards put a big emphasis on precision and stability.
Now let's jump across the pond and look at some European standards.
Okay.
Starting with DON 2080, also known as NMTB.
BN 2080.
NMTB, that's the National Machine Tool Builders Association. So another standard with some historical roots.
It is.
Okay. So DIN 2080 was an early standard for quick change holders.
It was, but it's not as common in newer machines
Okay.
as technology has moved on.
Okay, so what's the go-to European standard these days?
That would be DIN 69871,
Okay.
also known as ISO 73881 or SK,
Okay.
which stands for Steilkegel,
Steilkegel.
meaning steep cone in German.
Wow, you're really fluent in machining lingo.
I try. Steep cone. That makes sense when you think about how these holders fit into the spindle.
It does.
Yeah.
The SK standard is known for being really robust.
Okay.
And it uses an additional pull stud
Right.
for really secure clamping.
Got it.
And that tapered contact between the cone and the spindle makes sure everything lines up perfectly.
Okay.
All
So
right.
DIN 69871 or SK is a top contender in the European market.
It is.
Now, the book mentions another German standard, DIN 69893, also known as HSK.
Yes. HSK.
HSK, that's Hohlschaftkegel, which means hollow shank cone
Yeah.
in German.
Mm-hmm.
I'll get the hang of this. What makes it so special for high-speed applications?
Its short, hollow cone design allows for extremely high rotational speeds
Okay.
without sacrificing stability.
Right.
And it actually doesn't use a traditional drawbar,
Low.
which reduces weight and inertia,
Okay.
further enhancing its performance at those high speeds.
So it's all about minimizing those forces that could cause vibration or imbalance when things are spinning really fast.
You got it. But the book does point out that HSK holders require extremely precise manufacturing
Right.
because of those tight tolerances.
Got it.
They need to be handled carefully
Right.
to avoid any damage.
So, high performance, but also high maintenance in terms of precision.
That's a good way to put it.
Okay, we've covered a lot of taper standards, but the book saves the most innovative for last. ISO 26623, also known as KP2.
KP2.
Yes.
KP2.
It's truly in a league of its own when it comes to precision and stability.
Okay.
It features a polygon-shaped tapered interface
Okay.
and flange contact
Right.
for a super secure connection.
Wait, so instead of a traditional cone shape, it's got this multi-sided polygon. What's the advantage of that?
Well, that polygon shape creates multiple points of contact,
Got it.
which distributes the clamping forces more evenly,
Okay.
and it minimizes that risk of vibration or slippage.
So it's like a super secure, high-precision handshake
It is.
between the tool holder and the spindle.
You got it. It was developed by Sandvik Coromant,
Yes.
a leading cooling company.
They are.
They started with flange sizes C3 to C8.
Yes.
But in 2013, they added the C10 size, which opened up even more possibilities for heavy-duty machining.
They did.
So ShabyTO is constantly evolving to meet the demands of the industry.
It is.
That's impressive.
Yeah.
What are the main applications for this system?
It's a great choice for challenging components
Okay.
and multifunctional machines.
Right.
Especially when you're dealing with those long tool assemblies.
Got it.
It really shines when stability and precision are non-negotiable.
This has been an incredible deep dive into the world of work-holding systems.
It has.
I had no idea. There was so much complexity and ingenuity behind something that seems so basic on the surface.
It's a testament to the engineers
Yeah.
who are constantly pushing the boundaries of what's possible.
So to our listeners, if you're feeling inspired to learn more, I encourage you to keep exploring. Maybe dive deeper into a specific taper standard or research a particular machining challenge you've encountered. The world of machining is full of fascinating discoveries.
It is. And never underestimate the importance of a solid work-holding system.
Right.
It's the foundation for precision, for efficiency, and ultimately for success in machining.
Couldn't have said it better myself. Thanks for joining us on this deep dive into the world of work-holding systems. Until next time, keep exploring, keep learning, and keep those machines humming.